Hi everyone, welcome to this new video. We're gonna cover our ninth video of this series. And in this video, we're gonna learn a lot about rainfall intensities and distributions. So let's get started. On problem 3.6, we have using figures 3.6 and 3.7, we have it here on the right. Determine the average rainfall intensities in inches hour for the following time periods. So we have A through E that we need to solve. So we'll go one by one as always. And before I continue, I want to ask you to please react to the video. I'm I'm a student as well, and making these videos and explaining takes my own time, a lot of my own time. And the least I will ask from you is to react to the video so this project can keep growing and can reach to more people. Um, okay, let's start with part A. So part A, it says we're asked for the rainfall intensities in inches per hour for the following time, from 3 to 4. There are two ways to do this. We have to, I'll start explaining really quickly each one of these. So this graph shows us time and the average depth, so the precipitation depth. So what it's saying here is that in the first 15 minutes, there was 0.1 inches of precipitation of rain that fell. In the second 15 minutes, 0.11. In the third 15 minutes, 0.12. In the fourth 15 minutes, 0.15. Another way to see it is like in the first hour from 0 to 1, we have the sum of all of these in precipitation. So in the storm event from 0 to 6 hours, if you add up all these values, it should give you to a total rainfall of 6 inches. And these bars, what they represent is the intensity in relation to 15 minutes. So all of these values here, that's what, let me see, average depth. Sorry, this is not intensity. Actually, yeah, it is. Sorry about that. It is the precipitation in a span of 15 minutes. Precipitation amount in a span of 15 minutes. Precipitation amount in a span of 15 minutes. So that's what each bar of this, that's the value that corresponds to that. So that's how you read this graph. And this one here is the time hours cumulative volume precipitation in inches. So here they give us the amount every 15 minutes, the increments. Here they're adding them up. In the first 15 minutes, 0.1 plus 0.11 will give us 0.21, all the way up to until we get 6 inches of the total storm. So that's how you see this. And we're going to use these graphs now to solve. So they're asking us for the intensity from the third hour to the fourth hour. So if we use this, the cumulative graph, we can do the following. We can find the highest precipitation value at the end of the fourth hour, which will be, let's do this, that will be 5.01. We subtract with the lowest value at the beginning of the third hour, 4.44. Sorry, it will be 4.20, because that's how the third hour started, at 4.20. And then divided by the time that happened between these two values. So it will be only 1 hour. So technically you should divide that by the difference in time. So for part A, which is 1 hour, it's gonna be over 1. So this units of this will be 0.81 inches per hour. And that's the answer for the first part. Now for part B, now we're asked for the first half of the 6-hour storm. So it will be the first 3 hours. We do a similar approach when we do the last value of the third hour, 4.2, minus, in our case, would be 0 because it started at 0, right? All of that divided by 3 hours minus 0 as well. And So let's just do that in here. Divided by 3, it will be 1.4 inches per hour. Another way to do it with this other graph will give you the same results. It will be for the part A from hours 3 to 4. We want to know the amount of precipitation in that hour. So you just add up all these values in that hour. It's going to give you 0.81. Sorry, from 3 to 4 here. So you add up 0.24 plus 0.24 plus 0.18 plus 0.15, it's going to give you 0.81. And that precipitation was gotten during this hour. So it's going to get 0.81 per hour in this time lapse. Now, if you do part B for the first 3 hours, what you need to do is also add up all these values here for the first 3 hours and divide it by 3 hours, and you're gonna get exactly 1.4 inches per hour. So you could use both graphs, but in the second graph, you need to add up each value of them, find the sum of all of the values during that time. Here, you just recognize the highest value, the lowest value of the time interval, and then you divide it by the amount of hours. So I think it's a little less computation. So let's keep going. Part C will be the maximum in any hour. So in any hour, the maximum intensity is gonna be where the difference in precipitation is gonna be the highest. So I can see that here the slope is not as steep as from the second hour to the third hour. So I can already see that if I do 4.44, which is, no, it will be, sorry, 4.20, which is the highest value of the third hour, minus the lowest value of this, which will be 1.38, because that's how that hour starts, divided by 1 hour. It's gonna give us 2.82 inches per hour. So that's the answer for the part C, and that's the maximum intensity, rainfall intensity that happens in this 6-hour storm event. Now part D, they're asking for the maximum in any 15 minutes period. So all you need to do here is find the highest difference in bars, and these two are very similar, but part D. Okay, these two are very similar, but I already found out before I made this video that this difference, this minus this, is actually higher than this minus this. So let's just compute that. Equal 3.6 minus 2.46. And that's gonna give us 1, but we need it for a 15-minute period. So we're gonna have to go for 15 minutes is 0.25 of an hour. So you gotta do, it will be 2.25 of an hour minus 2, which will be at the beginning of this hour, of this part, right? So that's gonna give us 0.25, and you need to divide this by that time difference, and that's gonna give you 4 this was 2.46, not 2.6. Here 3.6 minus 2.46 is 3.6 minus 2.46, and divided by 0.25. So the answer is 4.56 inches per hour. And why? Because this is hours, right? It's 2.25 hours minus 2 hours. It's gonna give us 0.25 hours. If you divide both, you get 4.56 inches per hour. That's D. And then now we need to solve for the intensity in the last hour. E will be, intensity in the last hour will be this one here, right? So again, you can add up all these values here will be 0.12 times 4 and in that hour. So, or you can just do what we've been doing, will be 6 minus 5.50, um it would be 6 minus 5, sorry, 6 minus 5.52 divided throughout that 6 divided by 6 hours minus 5 hours, which will be 1. So it will be just 0.48 inches per hour. And that would be part D. So that's how you work with finding out intensities if you are giving a cumulative curve or graph, or if you are just giving the precipitation depths per interval. Okay, let's move on to the next one. Is 3.9. In this one, we're gonna graph different distributions. And let's see, 3.9 using the NRCS or SCS. They are both the same thing. NRCS is Natural Resources Conservation Service, I believe. And this used to be only Soil Conservation Service or something like that. So that's the same, and they develop these distributions. We're going to use the type 2 dimensionless cumulative rainfall curve that we find in Appendix 6. I already have it here. And we need to develop cumulative rainfall depths on an hourly basis for a total rainfall of 203 millimeters, which is about 8 inches. And we need to do the same for the Corps of Engineers standard distribution. So we need to generate a distribution curve using the SCS type 2 and the Corps of Engineers. You can use all these values here. Let me start by explaining this graph really quickly. So the SCS type 2, this graph here is normalized. Like if you look at the rainfall column, goes in this way, right? Time, finish here, and continues over here, and continues over here, and continues on the fourth column. So if you notice that the last value of rainfall precipitation is 1, which means it's normalized. This is done this way. So if you have, let's say, a storm where at the end of the storm it accumulated 80, it accumulated 8 inches, you can just multiply those 8 inches times 1, and not just times 1, but you multiply those 8 inches times every single of these values, and it's gonna give you the storm distribution. Now they didn't only normalize the rainfall precipitation, they also normalize the time. So it's also here shows 1. And what they did, let's say in the case that you want, for example, to know the distribution of the storm that lasted 24 hours, all you need to do is multiply those hours times every single one of these. So you have to multiply 24 times 1 will give us, for the last interval is going to be 24 hours. And then multiply 24 times this, 24 times this. So you're going to get a table of all those hours. And also a table of what would be the value of precipitation depending on the total depth of precipitation for every single time interval. So that said, I can move on to this graph here, and this one is actually easier because they already have done that. In our case, we don't have, they're asking us for an 8-inch precipitation. We don't have an 8-inch precipitation. We have 7.9, which is the closest we can get. And they already are giving us, for a 7.9 inches precipitation, they're already giving us the values. And the hours are already set up for a 24-hour storm. So all we need to do is grab the value of precipitation per every hour. And so we don't lose time, I already did all of that. So we have hourly, we have 24 hours. For the Corps of Engineers, I already grabbed, let's say, the 0 hour is 0. For the first hour, this time is in hours. For the first hour, we get 0.12. First hour 0.12, second hour 0.24. I already copy all this in here. You have to do that on your own to make the distributions. And then for the NRCS type 2 distribution, I already selected which one will be the hour. In my case, the first hour will be 0.011. So 0.042 is the first hour, and then 0.023 inches of precipitation will be for the 0.083. So you need to find which value represents each hour here. But I already have it here, so you can just match them. Now, these values of precipitation represent only 1 inch of the storm precipitation. So what we need to do is multiply each of these values times 8. So let's do NRCS type 2, 8 inches. That will be equals to this times 8. And this will be the values that we're gonna have to plot. So let me go over here. And now let's start plotting graph. Let's grab all our data, because that's how I've learned. I think it's easier in Google Sheets. If you're using Excel, I will do it differently. And then insert a chart. And we would like to do a line chart. I will choose a smooth line chart. And for the y-axis, what I want is, I don't want this. And the time needs to be in the x-axis. So we see something like that, which this curve, this part here shows me that maybe one of our values is not correct, but the x-axis is gonna be time. And yep, let's horizontal axis, name is time, and then the vertical axis is gonna be I don't that's not the intensity, that's gonna be the precipitation in inches. So what it means is that, let's say, for the NRCS type 2, for an 8-inch total precipitation, at 5 hours, we got about 0.512 inches. So this is over time, this is how the storm precipitation performed. And the type 2 shows that in the middle of the storm, at about 12 hours, the precipitation increased a lot. But at the beginning of the storm, it increases very slowly. And then the curves, it's a more smooth curves. So the change in precipitation volume is not as steep as the type 2. So that would be the comparisons. And I'm sure this part here should be a little more smooth. So hopefully when you do it, you get something similar. That should be good enough. Now, next problem, 314. It says develop a dimensionless rainfall diagram using the following incremental precipitation data from a 24-hour storm. So we're given the values for every 4 hours, and this is like the increments. This is not cumulative here. These are the increments. For the 0 hour, when we start with 0 precipitation, 0 water, 0 rain, and the next 4 hours, we have gotten 1 inch of precipitation. In the next 4 hours, we got 2 inches, and so on. Now it says using on one of the IDF curves, I have it over here. In a 24-hour, 50-year event, estimate the rainfall volume during the first 12 hours of the 24 hours using the dimensionless rainfall diagram you just developed. Okay, let's start developing the dimensionless rainfall diagram. Dimensionless rainfall diagram is the same as what we had here over here. This is dimensionless. What they call dimensionless, because then we just need to multiply. It works for any precipitation volume, because you just need to multiply whatever inches of rainfall. If you got at the end 2.67 inches of rainfall, you multiply 2.67 by each value of precipitation, right? So let's just start here finding. So we need to find, when we got this, we need to find the sum of all these values, which will be the total precipitation, right? So we got 10 inches. We're working with inches. In this storm, there were 10 inches. At the end of the storm, 10 inches of precipitation was accumulated. Um, or, yeah, was accumulated. So what we need to do to make it dimensionless, we need to divide each one of these values by the total precipitation. Okay, let me absolute this, because we're gonna use that for everything. Uh, so this 1 inch represents 0.1 inches dimension of our total precipitation. And now this will be the change in precipitation over, I would say this is like the change in precipitation over a total precipitation. So that will be inches over inches, which is dimensionless, right? Now, let's find what would be our curve for our storm distribution or our cumulative distribution. Cumulative would be equals to this 0, and this will be equals to this plus this value here. And now we can drag it. And as you can see, our last value is 1. And this is good because now we have it in the same form of our previous example or exercise. So whatever precipitation we got here, if we know the total precipitation was 10 inches and we multiply it by 1, we're gonna get 10 inches on our at the end of our storm. So this way we know how much precipitation we got every 4 hours as it accumulates until the end of the storm. Okay, I hope this makes sense. We have our dimensionless distribution now, which is here. And it says using the IDF curve for a 24-hour 50-year event. So we got 50 years will be the third from the top, the third line from the top right here. A 24-hour will be the last value, third from the top right about here. And if you follow that, it will give you about 3.9 inches, I would say, of intensity, inches per hour. And that's all we need this IDF curve for. So our intensity is 3.9 inches per hour. Now, using estimate the rainfall volume. So 3.9 inches per hour, that means that if we multiply our total precipitation over the 24 hours, total precip over the 24 hours is gonna be 3.9 inches over hours times hours is gonna give you the total precipitation times 24. That's gonna be the total precipitation in inches. Sorry, this is not 3.9, this is 0.39, because we get 0.39 right about here in the IDF curve. So we get 9.36 inches in the case that we get a 50-year return period storm. If the storm lasted 24 hours, the total precipitation would be 9.36 inches. And now we're asked estimate during the first 12 hours. So during the first 12 hours, that would be equal 2.6. And why is this? Why did I do 0.6 times the total precipitation? That's because the first 12 hours we have zero point 0.6 of the precipitation of the total precipitation. Um, how can I say this? Is like 60% of the total precipitation has fallen by the time 12 hours have passed. I hope that makes sense. So this will be your answer for the second part. 5.62 inches have been precipitated in this storm if it lasted 24 hours and it has a 50-year return period. Uh, this is what has fallen in the first 12 hours of that storm. Now let's move to the last problem of this video. Um, and this is just about following the IDF curve. So let's start. So part A, it says, using the IDF curve for Santa Fe, New Mexico, this one right here, answer the following questions. A, what is the rainfall intensity for a 50-year storm event with a duration of 60 minutes? So we got 60 minutes here, we go all the way up to the 50-year storm. And the rainfall intensity will be about, I would say, half between these two, 1.5 inches per hour. Oh, 1.5 inches per hour. Now part B, if the duration were 5 hours for the 50-year storm event, what is the total rainfall? So part B, you're going to, so for this part, you're going to do something similar. If the duration were 5 hours for the 50-year, you go 5 hours, 50-year will be the second line from the top. You will go to about 0.5, I will be saying it's 0.52. So if you do 0.52 inches per hour for times 5 hours, it will give you about 2.6 inches. And yeah, that will be the total rainfall for those 5 hours in Santa Fe, New Mexico for that event. Now, part C, if the watershed response were only 30 minutes, what watershed response means is equals to the duration or time of concentration. What time of concentration means is what time would it take for the farthest, for the drop of water at the farthest part of the watershed from the gauge, what time it will take for that drop of water to run all the way down to that gauge where it gets recorded. That is the time of concentration. In our case, it will be the duration or 30 minutes. It says, given that, what is the maximum 30-minute intensity using the 50-year storm event? So for a 30-minute, 50 years, we will get about, I have it in my notes that will be about 2.5 inches per hour. And for it says compare this to a storm with a frequency of once every 2 years. What it means is compare it to a 2-year return period. So for a 30 minutes on a 50-year return period would be 2.5 inches per hour. For a 30-minute storm in a 2-year return period would be just a little less than one, I would say is 0.95 inches per hour. So we notice that the more frequent the storm could happen, the intensity is gonna be less than a storm that happens less frequently, that could happen once every 50 years. If you're still struggling To understand what return periods mean, I recommend you to watch I believe the first or the second video that I made. I explained that pretty well. Part D, if the time of concentration for an impervious 20-acre watershed were 30 minutes, so our area given is 20 acres, time 30 minutes. What is the estimate of the peak discharge for a 50-year storm event? So we already saw for a 50-year storm event for 30 minutes was about 2.5. So that's the intensity for a 50-year 30 minutes event. Oh, that's not good here. That's 2.5 inches per hour. Now it's asking us what is the estimate peak discharge. So for outflow peak discharge, like maximum discharge, we are going to use the equation of Q equals CIA. And in our case, C, the runoff coefficient, will be equals to 1. And that is because we are given that the somewhere here I think it says impervious. Yeah, for an impervious 20 acres. So impervious means that no water is gonna be infiltrated. So that means that all the water is gonna run off. So 100% of it is going to run off. Now let's solve for Q. C will be 1 times I is the intensity in inches per hour times the area, 20 acres. So if you remember, in the previous video, we saw that inches per hour times acres, all of that equals to cubic. It's about the same as cubic feet per second, 1 cubic feet per second. So 50 inches per hour times acres is the same as, it's about the same as saying 50 cubic feet per second. And that's the answer for part D. And for the last part, E, we are asked what is an estimate of rainfall excess for the same storm as used in part D? Express your answer in cubic feet. So we have the rate of Q is 50 cubic feet per second, and that happens over 30 minutes. So all we need to do is convert all of this into for the 30 minutes and multiply it by the area because right now to get the volume, that's gonna be equals to 2.5, which is an intensity, times the 30 minutes of the storm times the area, which is 20 acres. And then we need to cancel out the hours and minutes. So we have to multiply by 1 over 60 and then multiply by 1 over 12 to cancel the inches, and then multiply by 43,560 over 1 to cancel the acres. So this is 1 hour over in 60 minutes. This is 1 foot in 12 inches, and this is 43,560 square feet in 1 acre. And that should give us our volume in cubic feet, which is 90,750. That's it for this video. I hope you find it useful. Good luck solving these problems.